Okay. Hello and welcome to the KISSsys web demo, where the focus will be on the efficiency calculation and thermal rating in KISSsys. My name is Cengiz Yilmaz, and I will show you first the efficiency calculation, then the thermal rating using dissipations, the temperature change over the oil over time, and last the combination between efficiency and load spectrum calculation. You have the possibility to write questions in the question window of the webinar tool on the right. My colleague Thomas Panero, who is responsible for development in KISSsys, will answer them live by writing during the demo. We will handle a couple of questions at the end of the demo, and I will read them aloud for all. Okay. So you have also some documents in the attachment of the webinar tool. So there you can find some instruction about what we are going to do. And also some paper where we did some scientific comparison between the calculation and the measurements. Okay, now first of all, I open KISSsys 2017. And open my model, which I prepared here for the demo. Okay, first of all, I would like to present you the model. So we have here two-stage helical gearbox with 3 shafts and some 6 bearings. And we'll use this model for the efficiency calculation because it's a simple model, but the main idea here is to show the functionality of our efficiency template, and it's the same for even complex models. Will be the same, this procedure which you have to follow. Okay, so first of all, what we're going to do is adding the efficiency template to our model. We have to be administrator first to be able to change anything in the model tree. We go to the standard templates, default templates, and we add here the efficiency template to our model. KISSsys will show then this template directly. You will see the interface. At the moment, I can close this default template window. And now I would like to first present you the interface of the efficiency template here. So on the top, you can see some result possibilities which you can have from this calculation, and there we have here 6 options, and we will go through all of them, so step by step, but here you can do this change. Then we have we are calculating according to the standard ISO TR 14179 part 1 and part 2, and I would like to change here to part 2. The main difference there is the definition of the housing, additional housing elements for the dissipations, and also the dissipation calculation itself. It's different, and I like it because it's more detailed here, and I would like to use this for during the web demo. Here you can change the units, and you can consider contact analysis if you like, but this will take more time than the standard contact calculation according to Niemann, contact loss calculation according to Niemann. So we will use the approach from Niemann. Okay, and here we will go from left to the right through all settings which you have in the interface. The basic idea is that you first define your housing, then you go to the additional housing elements, then you go to the ventilation if you have some convective air passing through over the housing surface. Then you have to define the lubrication, like temperature and the position of where how much oil you have in your system. Then you have to define the cooler power at least. So this we will do. We will go through all these points. So I just present first everything that you know where to click as well. So maybe you realized already that after I add this efficiency template that we add additional loss elements here in the model tree for every bearing and for every gear. The same you can also see here in 2D on the right side. The thing is, we need these loss elements to perform the iterative loss calculation in the shafts for the for KISSsys, for this efficiency calculation. But if you finished your efficiency calculation, efficiency aspects, then you can, and you want to continue with your model, you can just make a double click to reset, and all the elements will be deleted, and your model will be the same as before. So we have to change, we have to do this change to be able to make correct calculations. Then the report, you can just start the report. I will show you shortly also in one of the after one of the calculations with a double click of this button. Then now we go to the results. So results are starting here. We have the input power, output power, and the power loss. Here we can find the efficiency, the total efficiency and the efficiency of the gear mesh. And down on the left hand side we can find the losses listed, like churning losses of the gears, meshing losses, bearing losses, and seal losses. On the right corner we can find the dissipation from housing, foundation, shafts, and the cooler power, and the oil cooler, yeah, and the total dissipation. So this is the interface in shortly, as I showed you just quickly. And now I would like to, as I told you, first go to efficiency, just calculate the losses of my system, but first by doing first the housing definition. So we can double click here on housing, and I can find here some housing settings first. The first window is just geometry. I have a rectangular or cylindrical shape which I can use. This is defined in the standard like this, so we cannot use different type of geometry, but for sure you can define the length, and you can change then the area. I will show you this next window. Here is the definition of the wall thickness of your housing. Then you have some extensions, which is the distance from the machine element to the housing, to every housing wall. And here at the moment we say, okay, the housing starts directly where the gearbox ends. So, but we don't give any space there, but we will see if it's needed or not. Then here we can define if the coupling is inside of or outside of the housing. And let's say we assume that it's outside. We click on OK. In the second window, KISSsys is showing us the dimensions of the housing with length in X, Y, and Z direction. And as I told you before, you can change now here the total area. If this is not fitting to your application, you can change it. Just you have to calculate for sure the other length. So this is important that you do, but you can adapt it to your application in this way. Let's say we are happy now with this for our web demo. And next point you can we have to use is the surface treatment of the housing. Actually, this is changing just the emissivity, which is the ratio between housing temperature and lubricant temperature. And for painted surface treatment is the highest, and the rest is lower than painted. So the next settings, this is more graphical thing, that you want to see the housing in 3D, you want to see the oil level, and if you want to add some seals at the bearing positions, this can be done here automatically, but for this basic calculation I don't add it now. Okay, so this point is ready. Next point are the settings. If you go there, you can define the housing more detailed, the detailed elements of the housing according to the standard part 2. So thermal fins, foundations, and input-output shaft. And you can click here. There is also an option to set the heat transfer coefficient manually if you like, but we would like to have it calculated. So now next windows will be about thermal fin, foundation, and input shaft. So if I click on OK, these are the inputs for the thermal fins, and I can show you a picture there from the standards. So about the thermal fins here. So we have to define the height, the thickness, the projected area, and the ventilated area according to these inputs here: projected, ventilated, height, thickness, and the total surface area. So these inputs are according to the standard, as I showed you before. Let's say that's fine for us. It's good prepared. Okay. Then next point is the definition of the foundation geometry, where the first point is the material, then the heat dissipation over in both directions or just in one direction. And here these inputs are again according to the definition in the standard, and I can show you this as well here. So we have here the foundation, here is the gearbox, and the different plates are marked with the lengths of these plates are marked with L1, L2, L3, 4, and so on. So we have to define these lengths to be able to define this area, and you define the height here according to this graph. So this is a good start for us. And then the input-output shafts is also according here to this drawing, just basic. We have the length and the diameter of the shaft and of the couplings. So here I can initialize all values to take the values from my model automatically to this menu, or you can also change this. You can change the thermal coefficients here manually, and you can also change diameter or length if you want to calculate something different than what you have in the model. Okay, so second point also finished. Then we can go to ventilation. Means this is the ventilation to have convective heat transfer over a surface, but you can define the plane, and you can define the air velocity, the ambient, and the ventilated air temperatures. But we don't want to, in the first step, we don't want to consider a ventilated surface. Let's say no. And about these planes, you can see in 3D now, if I check the settings for the foundation, you can see here what is created. And about these planes, you can just activate the coordinate system, and then you see where is X, Y, and Z, and which plane is meant if you go to this menu here. Okay. Next point is the definition of the lubrication. If you define in your model previously that you have oil bath lubrication, then you will see the settings for the oil bath lubrication. If you defined the oil injection, you will see that one for sure. So here I go to lubrication, and I say this oil temperature I would like to set globally. So let's say yes, then this is going to all calculations in my model, to all gear pair and shaft calculations, and will be set to 80. Connect oil level, I would like to use this, I would like to consider the oil level globally. So this will affect for sure the oil level in the different shaft calculations, but this is the correct way actually. And oil bath setup, let's say I let it calculate. You can also define here the oil level, and calculate is taking the highest bearing and put it into the middle of the inner and or outer race. Okay, so like this with these definitions. And last point is the oil cooler. Here I have the cooler power and the temperature drop over the cooler. But let's say I don't have any cooler here. Just make OK in the first step. And now we can check the 3D viewer, and you see here the oil level. As I told you here, this is the highest bearing in Z direction, and we set the oil level in the middle of the inner and outer race. And we defined here in lubrication that we want to connect the oil level, and this has an effect here. For example, if I go to shaft 2 calculation in KISSsoft, and then here I see that this oil level is automatically set with this setting which I do there. Okay. So now it's time to do our first calculation, which is we would like to see first just efficiency with these settings which I did before. So just go here, calculate efficiency, and we can click there to get some results. We have some iterative calculation, so that's why it takes a bit time. Okay, and then we can see here the input power which I put in here, 3.6 kilowatt, and I have a total efficiency of 96.01% and gear mesh of 97.38. On the left side at the bottom here on the corner, we can see all losses, 39.3 watt for the churning losses, for the meshing losses 94.8, and so on. So as you see, the dissipation is not calculated, so we have just the losses because of this setting here. Yeah. Now, this is the situation for the losses, but I would like to see now how I am in the thermal balance, means if I do I have also enough dissipation if I have such losses. So let's change here now to heat transfer and check also about the dissipation. Okay, then I see, okay, I have total dissipation of 107.6 watt. So in total, I have about along the housing, I have the highest dissipation. That's it's expected as expected, and here I have a difference of around 40 or 37 watt. So now there are a couple of things which can be done in this system. So either we say I would like to install a cooler power because I don't want to change my oil temperature should not be higher than 80 degrees. So then I have to select cooler power here and get the result for the requested cooler power which is needed here. And if you have, as I told you in the beginning, if you have any questions, don't hesitate to write. My colleague is answering them live. So the calculations finished. Now I wanted to have the required cooler power to have thermal balance, and this has happened now here. I can see that I would need 36.5 watt to have thermal balance, and this is now a decision. If you say, okay, I can install this cooler and then you don't have to do anything. You can keep the lubrication temperature, the oil temperature of 80 degrees. But maybe you say, no, I don't want to install a cooler, so we set it back to 0 watt here. And now I would like to see, okay, how much is the temperature change of my oil in this situation to have the thermal balance. So then we can do the calculation again. Now this is again an iterative calculation, that's why it's taking a while until we get the results, because it's increasing the oil temperature and checking if the condition is in thermal balance, then increasing again, and so on. Okay, so we reach the mount for the losses for 145.2 watts and for dissipation as well, more or less the same, at the oil temperature 98 degrees. So our oil temperature will be, if we wait enough long, will be at 98 degrees. In this case, and if you say no, this is too high, I should not be higher than 80 or 90 degrees, then we have to have other solutions. You have to find other solutions, or simply we say, okay, I want to keep 80 degrees and I want to keep this design. I don't want to change anything in the housing or something. Then we have to decrease the input power, and this option is calculating you for this configuration the maximum possible input power to have the thermal balance. And this is again an iterative calculation, so it can take a while. And in the meantime, you can write questions as well at the chat or question bar, which you have on the right side in your webinar tool. So it's trying to find the balance between dissipation and the losses. Okay. Now we see we have a total loss of 108, around 108 watt at 2.3 kilowatt input power. So we had 3.6 in the beginning, so we have to reduce really 1.3 kilowatt in order to have the thermal balance. So these are the results now. This is the situation actually. If you want to keep the oil temperature, so what we could do is now just say, okay, I want to still keep 80 degrees and I don't want to use any cooler. So we have the other option is now to change some, either we reduce the losses or we increase the dissipation, because it was to 140 to 100 around. So we can increase the dissipation by increasing somehow the housing geometry, the housing surface, let's say. So I go to housing, and at the moment I have no extension. So let's say I give an extension of 7 millimeters everywhere. Okay. So I can size this. This I can keep again, these settings. And then we can see the 3D view. So you see now here, the housing is not directly attached to the gear or here to the shaft. There is some space. And we can do now the heat transfer calculation. So we just want to check the new situation now without thermal balance. So we have 80 degrees here, that's fine, and no cooler. But we increased a bit the housing geometry, and then we can calculate again. Yeah, now we see, yeah, we reach around 130 watts, so that's already close to the losses. So like this, just now increasing maybe also the foundation geometry here, or increasing the thickness of the foundation, or the length of here of these plates, of these two plates, will already maybe be enough to have the thermal balance. So I could go to the settings, for example, again, and change not the thins, but the foundation geometry, maybe also here to 40, and here as well to 40, and the height maybe to 15 millimeters. So just to check how much is the influence there, and then we can do the calculation again. It can take again a while. So now you see we are at 134. So this, you see, about without any cooler and without changing at the oil temperature. I mean, now this is 80 degrees. Now if I switch to oil temperature with these settings, it will be not so higher than 80, so maybe we are already below 90 degrees, and this temperature increase of the oil can be still accepted in your design, maybe. It's trying to find the equilibrium, the balance again. Okay, and yes, it's just a 2.5 degrees of temperature drop, so could be still acceptable if there is a limit of 90 degrees. Yeah. The other option would be to decrease the losses by changing different bearings, or by checking the contact of the gears, by reducing the oil level, and so on. Okay, so this was until here. We had already the 5 options. Now the last one here in this menu is the temperature per time calculation. And here I would like to set my temperature to 50 degrees. And using here the temperature spectrum, so I don't change the setting, I don't change anything in my system, my definition. Let's say this is our design which we want to continue, and now I would like to check the change of the oil temperature over time. And I go here first and go to definition dialog, and I define 6 bins here, and let's say factors and in hours, that's okay. And the speed and torque is defined at the input of my system. Okay, then it's automatically opening this table where I can enter my steps. So let's say I have 0.03 hours, which are 1.8 minutes. We have to have very small steps here as possible, small steps as possible, to have a stable calculation. So in total I have 6 times 1.8 minutes is around 10.8 minutes. And I say, okay, I have active everything. My motor is on from the beginning and running with the same torque and speed always for every bin. Okay. And then, so we have 2 settings we have to take care. The first one is to have here temperature per time, and the second one is to set here the starting temperature. We go to temperature spectrum, and we can run the efficiency calculation again with this requested result setting. The system is now, first, before it starts with the calculation, we have to define for sure the housing mass, the foundation and the input shaft mass. for the dissipation, the dissipated elements we have to define, and we have to define the specific heat capacities of these elements. Okay. Now what it's doing is taking this temperature which I defined and calculating the heat dissipation or the generation of the heat, and calculating the temperature which is which is active then, and this calculated temperature is the new temperature, new starting temperature for the second bin, and so on. So it takes for a while, but it's doing now this 10.8 minute calculation. Now you see, after these 6 steps, I start with 50 after the first bin, after the first 1.8 minutes. It's 51.85 and then increasing until 59.67. So I have around 10 degrees Celsius. I have a difference from the starting and to after these 6 steps, after these 10.8 minutes. And what I would like to do now is, first we have to be careful that this last temperature is set here in lubrication. So if we want to start again with 50, we have to go here again and set it back to 50. And I say, okay, in these 2 steps, in step number 3 and 4, I just stop the motor and I don't run it. So I would like to see how much, how big is the temperature there in my oil, my gearbox. And then I run this again. So be sure that here is temperature on time. Here is 50 degrees. I already said before, and then run the efficiency calculation. So it's asking again about the masses and about specific heat capacity. Just click on OK and run the calculation. So as you will see also in one of the papers, there are some applications where they check or they want to calculate how much they have to turn off the motor, that it doesn't increase, goes above any specific temperature. So this can be also analyzed with this tool, where you can shut down, take off, shut down, and then check how big is the temperature increase in total then. So it's doing the same iteration again with 50 degrees starting, and here with switching off the motor. Yeah. Now we can see here that I started 50 again. I go up to 51, 53, and then after these 2 steps I switch off the motor, so the oil temperature is going down, the oil is cooling down to 52 to 50.68 again. And if I switch it on again, switch the motor on again, and then I increase the oil temperature to 54.2. So like this we can have some analyze about this temperature development or this temperature change over the time of the oil in our gearbox. Okay, so this was the 3rd point in my presentation here, as you see. And now we go to the last point, efficiency calculation with load spectrum. So it's a combination of the efficiency template and the load spectrum template which we have in KISSsys. So what I do here, close, and before I do this step, I would like to show you also some results of this calculation. So if you do some efficiency calculation and you would like to check the results, the first thing is you can check the report here, where you can find a summary first about global results, the generated heat, the dissipated heat about around the elements, and second point, the settings which you set for this calculation, and all the individual power losses here in the report. And this table is a very nice tool actually, because if I go out here, you can also see this in KISSsys. If I close this and go to the losses table here, you can also see this table here, and you can find all elements listed and all the losses from them, and you can detect which one is the highest and lowest, which one is generating the highest and lowest loss. And I can see here, for example, for the gear contact PVZ is gear 1, 2. This mesh is generating the highest gear contact loss. For the churning losses, I see here that here gear 4 is generating the highest churning loss, 15.6. The rest is 5.7, 10.1 watt. So, and for the bearing losses, I can see here that more or less all bearings are creating this 3 watt, around 3 watt. So I can detect just here my element, which the most generated loss elements in my system. So this is a nice tool. And here about 1-2 words about the correction factor. This is more a calibration between your measured system and the calculation. So if you see now, if you see in your experiment, okay, the churning losses are 20% more higher than here calculated, then you can go to the correction factors for the losses, and you can go to churning losses. You may go to ES and define here factor 1.2. Then you have a 20% higher value there in the results. So you can press OK. And if I calculate now with this configuration, just the heat transfer maybe. It's running with this, with the same settings before, just with the latest lubricant oil temperature, which I had in the table before. So now it was around 54 degrees, and now I have here 42.7. If I go to the losses, so churning losses, yeah, it should be PVZ0 here. Yeah, I have here PVZ0 is 15.6 in normally just for this gear, and I have 20% more here, and this is the current value. So you can adapt like this the measurement to the calculation. The same goes for the other gears actually. Here. Okay, so after also describing the results, I would like to go to the last part. So now you would like to see, okay, with this load was the losses, I know more or less the losses, but maybe you would like to create a field, a loss field, using different loads and different torque and different speed. And this can be done using the load spectrum template in KISSsys, and it's much more nicer documented also in the new 17 version. So I'm using now the KISSsoft KISSsys 2017 beta version at the moment, and here you will see what is implemented about the results for the individual losses for every element, pin element. So now what I do first is I add to the root directory from the default templates a load spectrum. So it's a load spectrum template. Then I can close this. And I can just define maybe 2 steps just for the presentation now. Right mouse click, definition dialog, and define 2 steps. And frequency in fraction is good, so total is 20,000. And the speed and torque should be defined as input factors. And the reference is the input values, or the input values which are defined also in the boundary here. Click on OK. This is just that these different parameters are different from the initial kinematic calculation, but we can replace them with the reference values. Okay. And then let's say in the first step, then we will just want to calculate the efficiency and would like to just see the losses for every bin. And I say here I have 70% this amount, and here I have 30% amount for this load, and for 20% more load, 1.2 torque. And here let's say is 0.8, and here 1 speed. Okay. And then depending on what you would like to see, now I just want to see the losses, so efficiency is enough. And the rest you don't have to set here, just important that you have the configuration which you want to calculate. You can go to load spectrum template, and here with this button we can run the calculation with load spectrum from the template. So I can click here, and these template settings are also changed a bit in the 17 version. So we already did some explanation about this in previous web demos. So the change here is that we have here that you can consider more during the load spectrum calculation. So now if you have considered power loss from efficiency template, here it's no, but we can switch it to yes. For our example, I don't want to see the full report. I'm not interested in the strength actually at this point, and I don't want to export KISSsoft files or execute contact analysis or use housing stiffness and so on. So these are all new options. We can consider housing stiffness. We can consider also model analysis for every bin and so on. That's good. Yeah, just efficiency with the spectrum. Okay. And then this can take longer, for sure, longer than a normal load spectrum calculation, because we are doing the standard load spectrum calculation, and in addition, for every bin, we are going to the efficiency template and running the efficiency calculation for every bin. So that's why. So now it's bin 1 is more or less finished. And yeah, that's the reason why it's taking longer than just with the load spectrum calculation. But the nice thing is you have in once after the calculation, when the calculation finished, you have in once all results saved in the folder. So you can go to your folder where the model is saved, and here I can see that KISSsys created a result folder here again, as it is expected from the load spectrum calculation. If I open this, I have the results and the damages. And the results are at the moment not saved, but they were saved before, so I can show you one calculation before, and you will find efficiency template result like this, and you will find for every bin the results here, the losses as expected. So this is my prepared file, but normally it is writing out like this. So I can see for bin 1 the losses for the gear, for the bearings. This is for the load dependent gears, and this is non-load dependent losses for the gears. And the same will go for the dissipation. If you activate heat transfer there, we will also write out the heat transfer for every beam, the dissipation for every beam. Okay, so this is the procedure actually, and also a bit for you to see with the new things in 17, the new features which are especially in the combination of low spectrum in 17. And yeah, thank you very much for attending first until now, and now we would like to I would like to present you some questions, or from the general questions, some good questions here. I have the list in front of me. Is there a possibility to calculate the losses for a certain load, torque, and input speed instead of input power? Yes, the losses calculation depends on the speed and torque defined in the boundary condition. The input power here is just displayed for the balance. It is not a setting. Yeah. Second question, how would you approach more complex housing models which are not rectangular or cylinders? Do you just use CAT to calculate surface area and give an overall length, width, and height? And that's exactly the case. So you can simply enter the total surface area for your housing to calculate the heat dissipation. The shape is only used for the churning losses of the gears, but can be approximated. And third question, which is also maybe also a good one, is it possible to define the input shaft as a heat source, where it could be a shaft connected to a hot electric motor that is putting heat into the gearbox? Yes, if you set the cooler power as negative, you can bring heat inside the system. Yeah, basically that's the simplest way. But what is also maybe possible is also use the correction factors and have higher loss in the system. Yeah. Maybe a last question, and then we will close. So one of the good ones. Yeah. Yeah. Just maybe if the preloads in the bearings are taken into account in our calculation, and it's like that everything that is considered in the bearing calculation method here, it's SKF 2014, is considered in here too. Yeah, that's it. Okay, so yeah, thank you very much for attending to the web demo in general. Now, if you have additional questions, you can write an email to info@kisssoft.ag. We will have additional web demos for KISSsys in future for sure. So keep checking the website, and not to forget that we have some trainings also in March. So in March we have 7th to the 8th March we have shaft and bearings trainings, and from the 21st to 22nd March we have KISSsys industrial gearbox training 2 days, where we also show these things in the second day of this training. So it can be also interesting. And information about the schedules in general for the trainings you can find on our homepage. And as I told you before, information about the calculation efficiency template in KISSsys, and also about a paper you can find in the attachment of the webinar tool. Yeah, that's it actually. So I wish all of you a nice day or evening, depending on where you are, and I hope to meet you next time. Thanks.